Hi, this video will talk about another idea in rotation, and this is going to be called rotational inertia or moment of inertia or rotational mass. And in the past, we said that if we roll two things or if we slide two things, mainly rolling, if we take a marble or two marbles, one heavier than the other, and we roll them down a ramp, which one is going to get to the bottom first. In the case of the marbles, they both will reach at the same time. But there different shapes will reach the bottom at different times. So this is what I mean. So I'm going to do a demonstration here. I have a filled-in disc, okay, and I have a hoop. Okay, so all the matter is concentrated on the outside here, and the mass and the matter here is evenly distributed. So if I roll them from down here, okay, based on what we've learned so far, we always said that they're going to reach the bottom at the same time because they started with the same height. But until now, we haven't mentioned rotation. We didn't take into account that these objects are actually rotating as they slide in down. Okay, and speaking of sliding down and stuff like that, if this surface is frictionless, these objects will not roll. And here is the reason why they won't roll. So you have an inclined plane, you have an object that's circular, right? Now let's look at the forces acting on this. This is the center of mass. So you have a normal force. See, up to now, we say, well, the normal force is from the surface because we considered every object as a particle, as a dot. Okay, but now these objects have shape to them. So we can't just ignore the fact that they have shape. Okay, and then you have your mg. Okay, and your axis of rotation is right at this dot and it's coming at you right along the marker. So if you think about it, mg will not generate any torque. That mg is going right at the axis of rotation. The Fn will not generate any torque either. So basically, this object will just slide down if there is no friction. But if there is friction, friction will be acting up this way. Okay, and you are this far away, you are at a distance r, the radius of that object, from the axis of rotation. So F will generate some torque. So just keep that in mind, that friction is required here for us to roll down the ramp. Otherwise, we're just going to slide. So if I let these two go down the ramp, okay, we're going to see which one is going to win, and we're going to try to explain why. Okay? Okay, and you can see that the filled-in one wins. And the reason for that, it has to do not just with the mass, and when we do energy, we're going to find out that the mass of these objects doesn't even matter, and even the radius doesn't matter. Okay? What matters is how the mass is distributed. See, the closer the mass it is to the axis of rotation, the faster it will go. So in this case, in this one here, the mass is distributed further away from the axis of rotation, which is right here. So we say in terms of rotation, we say that this is lazy to rotation. The mass is further out. Now, when we talked about pendulum, I'm going to do a couple examples here. When we had a long pendulum, the axis of rotation is right where my hand is. It's coming at you. So when we did this, it took a long time for it to oscillate. But when I made it shorter, when I made the mass closer to the axis of rotation, it went pretty fast, if you recall that, right? It goes pretty fast. Another example is if you take this thing that I made, and it has 500 grams at the ends, and if you try to rotate it, and we'll try to do this in class, okay? It actually feels harder to rotate than if I get the masses closer to the axis, and it goes pretty fast. You probably can see that in the video. I'll let you try this in class, and I'll let you try some other things. Okay, so the moment of inertia, or this rotational mass, every shape has a moment of inertia, so that we call I. Okay, and there is a table or Yeah, there is a table in your on page 27 in your packet, okay, that gives you pretty much the I for all the shapes, and it all depends about which axis they are rotating, and we'll look at that in class. One thing I want to talk about is, in the case of a pendulum, for instance, if you have an axis of rotation here and you have a mass that's further away, if you want to find the moment of inertia, let's say this is attached with a massless string. The moment of inertia of this is just going to be m r squared, r being the distance between where the mass is and the axis of rotation. So that's the same formula for a hoop. So the hoop and the single mass will follow the same rule. And I'm going to just do one example, the one on page 28, and that's number example 811. So we have a 5 kilogram here. We have the axis of rotation here, and we have a 7 kilogram here. Okay? Yeah. And this is 2 meters, and this is 2 meters. So if you want to find the I for this, you have to find the I of all your components and add them up. So this is a single particle, so it's going to be m r squared plus m r squared equals, that should be equal to 48. Now what are the units? Well, it's m r squared, so it's kilograms, meters squared, kilograms, meters squared. Now the other shape that we have is the axis of rotation is here, and so this is the 5, this is the 7. Okay, this distance here is 4, and this distance is half. So the I for this one is just going to be 5 times 0.5 squared. So this dotted line is the axis of rotation, plus 7 times 4.5 squared. Now if you do the math there, you should get 143 kilograms times meters squared. So what does this mean? It means that it's harder to rotate the bottom one than it is to rotate the top one. Okay? So the higher the moment of inertia, the harder it is to rotate an object. And going back to the hoop and the cylinder or a disc, okay, the moment of inertia of this guy here is 1/2 mr squared. So this is for the disc. For the hoop, it's just mr squared. So there is a 1 here. So this coefficient 1 is higher than the 1/2. So it's going to be harder to rotate the hoop than it is to rotate the disc. That's why the hoop takes a longer time to get to the bottom, because it's lazy to rotation. It doesn't want to get to the bottom. And we're going to do plenty of demonstrations in class. All right, I'm out. Peace.